Welcome all the viewers to a fascinating journey into the world of quantum field theory. Today we are going to explore a fundamental concept in this field that plays a crucial role in understanding the behavior of particles and fields at the quantum level, the Lagrangian. But before we dive into the Lagrangian, let us set the stage. You see, the quantum world is full of surprises and quirks that challenge our classical intuitions. So we will touch on some of these fascinating ideas today, like spontaneous emission and the limitations of Schrodinger's equation. So what are these limitations and how does Lagrangian come into play? Well, stay with me and we will uncover the secrets of the quantum universe together. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to part 5 of demystifying quantum field theory, where we would be going deep into understanding why do we need Lagrangian right at the beginning of studying QFT, and what are some of the concepts like Dirac equation, Schrodinger's equation, and some of the limitations of these equations. Before we go ahead, those who have missed my part 4, I put it up in the I button, but here is a kind of a quick understanding. Well, these are few of the quantum field theory lectures. I mean to say these are live lectures which are there on my live tab of my channel Physics for Students. You can go through that. These are more mathematical in nature and I do conduct this type of live lectures on the evening. So if you want to understand, talk and get a kind of a discussion in clearing some of the concepts of quantum field theory, you're welcome. I announce the dates on my channel Physics for Students when I'm coming online. So already I have done around 5 to 6 lectures. So first, a quick recap on what are the things. If in case you have missed, you don't have to worry, because here is a quick recap, a whirlwind tour in understanding the important concept that we did in the last episode very quickly. So first what we did is that we understood what are the differences between classical waves and quantum waves. So as you can see, the first difference is that quantum wave function is not observable by itself if it allows you to compute the probability distribution observable. So here the waves are often described by classical wave function. Classical waves are typically characterized by amplitude and frequency, and classical waves can carry energy and information. Whereas quantum waves, the quantum plane waves, are fundamental concepts in quantum physics. We learned that plane waves are solutions to Schrodinger's equation, which is the fundamental equation of quantum mechanics. And unlike classical waves, quantum plane waves are very probabilistic in nature and hence they do not carry energy. And quantum plane waves are characterized by their wave function, which is obviously a complex valued function. This is just a kind of a overview, but if you want to know more, you can go to part 4 of quantum field theory. It is there in my playlist of quantum field theory lectures. But one difference is particularly noteworthy, that the difference is that it only allows to compute probability distributions for observables. Now there are other important differences such as entanglement and others. So if you need to describe two particles, for example these two particles with the help of a wave function, classically you might expect one of the two possibilities. On the one hand, you may think that they can be expressed by some two wave packets of the single classical field psi x, this one. On the other hand, you may think that they are basically two separate particles, psi 1 x1 and psi 2 x2. So you can treat them as two separate particles. The quantum reality is more interesting. You have to describe them by single wave function depending on both coordinates, generally not factorizable into separate pieces. But in case of quantum, I would say when you are dealing with the traits of quantum behavior, so you see that this actually these separate pieces are something which are not always equal to. So in quantum mechanics, a particle is described by the wave function psi, which generally is a complex valued wave function, and the wave function always need not to be a wave. So here you can see the quantum reality is something more interesting. You have to describe them by a single wave function depending on both coordinates, generally not factorizable into separate pieces. So this is the basic difference that we saw earlier. We also saw some of the fundamental difference like determinism and probabilistic nature, because classical waves are deterministic and can be precisely described using continuous mathematical functions, while quantum waves are probabilistic and described by the likelihood of finding particles. Classical waves can carry energy and information as they propagate through space, whereas quantum wave planes are the probability distribution of particles. The classical waves are typically described using classical wave equation, whereas quantum waves are described by using the Schrodinger wave equation, and quantum plane waves are manifestation of the wave particle duality, which implies that particles exhibit wave-like behavior of the quantum level. Classical waves do not exhibit particle-like behavior. So we can summarize all those which we have told in here, that in summary, classical waves are continuous, deterministic, and describe the behavior of microscopic waves, while quantum waves are probabilistic, representing the quantum behavior of particles with wave-particle duality. We dealt with this, and also what we found over is that we went from classical field theory to quantum field theory. That means, say for example, if we get a classical field theory, which is a branch of physics that describes how physical fields actually interact with matter. So here you can see that here basically what is happening is that the physical fields are interacting with matter, and a physical field is a quantity that is assigned to every point in space-time. So this blue line, you can see all those black arrows, they are pointing at every point in space-time. Examples of the physical fields include the electromagnetic field, the gravitational field, and the Higgs field. So from here we understood that classical fields are typically formulated using the Lagrangian formalism, and the Lagrangian is a function of the field and its derivative. So we can summarize that classical field is a theory, is a branch of physics that describes how physical fields interact with matter. Whereas on the other hand, what we understood is that quantum field theory is a branch of physics that describes how physical fields interact with particles. And a particle is basically a localized excitation of a physical field. For example, an electron is an excitation of the electromagnetic field. It also tells that fields are treated as quantized quantities. That means fields can only take certain discrete values, which actually are typically formulated using the Hamiltonian formalism that was basically done through Lagrangian formalism, and the Hamiltonian is a function of the field and its conjugate momenta, and hence it describes the energy of the field. So this was basically the difference between classical field theory and the quantum field theory, how we move from classical to quantum. This one describing the physical fields interacting with matter, and quantum is telling that it is describing directly with particles. We also noticed in the last video that there are certain changes in terms of equations of motion. Equations of motion in classical Lagrangian and the Euler Lagrangian equation. Here we explained the Euler Lagrange equation. Here is a quick understanding. So this one is basically the partial derivative of L with respect to xi, and xi is the generalized coordinate, also known as the generalized momenta. This part actually represents the time derivative of the generalized momentum with respect to time, and it is the time derivative of the partial derivative, whereas this xi is how the momenta associated with coordinate changes. This part actually tells the term represents the partial derivative of the Lagrangian with respect of the generalized coordinate xi. This is the partial derivative of L with respect to I, and this 0 is the consequence of principles of least action. If you go back, I have also explained how the contra and the covariant vectors actually are denoted by the upper and lower indices. However, I am ignoring this for the time being. We also saw in the last video that this equation leads finally to this kind of an equation, and it actually tells that the Lagrangian L is in both way leading to equations of motion, and equations of motion are leading to the Lagrangian L, and also these equations of motion are leading to Hamiltonian, and the Hamiltonian can be traced back to equations of motion. So finally what we can tell that either we know the Hamiltonian or the Lagrangian or the equation of motion, we can actually deduce either of them. That means this is a convenient way to show that how we transitioned from the classical field theory or classical philosophy to the quantum philosophy, where we know each of the variables and we can deduce the other. What we also saw is that there is a transition in terms of equation, typically from classical to quantum field theory. As you can see, the classical field theory is analogous to classical particle theory. Instead of the Lagrangian L, we have a Lagrangian density, which is a curly L. And instead of time as an independent variable, we have these factors, x mu equal to 0, 1, 2, 3. And also where we found that xi is independent variable, instead of particle describing as x side of t, we have a field described as phi x mu, or we can say this one, where this r actually designates the electric, I would say electric and magnetic field, or I would say that it would be different spatial components of the same field vector like E or V. So these are actually, I would say, different ways in which we saw the transitions from classical to quantum field theory. We also saw how these equations changed from these different notations going to field, and the Lagrangian now changed to Lagrangian density. We also tried to understand in deep that what is the Lagrangian density and why it is considered to be so important. So Lagrangian density is basically, consider this as a fundamental concept of quantum field theory. It is a density function. So if you see this is a field, it is a density function defined in terms of fields and their properties over space-time. So Lagrangian density actually plays a very crucial role in quantum field theory and distinct from the classical Lagrangian here. So in classical mechanics, the Lagrangian is a function of generalized coordinates. These blues, for example, these are certain points. And what we found is that in classical mechanics, it is usually represented as this, where Qi is basically the generalized coordinates. And in quantum field theory, instead of dealing with, you see this blue, those things which I just showed you, these are in terms of classical. But in quantum field theory, what we do is that we deal with something which is a field. So instead of individual particles, we work with fields such as scalar fields, vector fields, and tensor fields, which are continuous over space-time. And the Lagrangian density is a function that on those fields and their space-time. So here we say phi x, it represents the field, and this part actually represents what is called the space-time derivatives. So we actually made a pause and we tried to understand the importance of Lagrangian density. And now we come to today's video. We start from here, and what we do is that, okay, so the equations of motion, yes, are also important because it is the deriving point for deriving the equations of motion. Lagrangian density is used to define the action, which is a central quantity in quantum field theory, and also the symmetries in terms of the Lorentz invariance and gauge invariance is also very important. So now we start with today's video, which we are starting right from now. What we are going to learn is that we are going to look into what is the limitation of Schrodinger equation in order to explain a phenomena which is very common, which is called spontaneous emission. And until we understand the limitation of Schrodinger equation, we won't be able to understand the further equations, why it evolved in terms of quantum field theory. So right now, coming up, what is the limitation of Schrodinger equation? And before that, I need to explain you a physics phenomena which is called spontaneous emission. So spontaneous emission is basically, you can say it transits from an excited energy state, which is in the top, to a lower energy state, which is at the ground. And during this time of excitation from the energy higher to lower energy state, it emits a quantized amount of energy in the form of photon. Now, I would request you all to pay attention to this definition, because this is the central part from where there is a limitation of Schrodinger equation we will deduce. So it emits a quantized amount of energy in the form of a photon. So spontaneous emission is actually responsible for all the light that we see around. For example, fireflies produce light through a chemical reaction that takes place in their abdomens. So the reaction actually for fireflies excites molecules in their bodies, which then emit photons of light, and this is an example of bioluminescence. Neon lights are filled with neon gas, which is excited by an electrical current. The excited neon atoms emits photons of light, which gives the neon sign its characteristic red glow. The incandescent, I would say, light bulbs, they produce light by heating a filament to a high temperature. The hot filament emits photons of light which give the light bulb its characteristic glow. The light emitting diodes are semiconductor devices that emits light when they are passed through an electric current. The light is produced by the recombination of electrons and holes in the semiconductor material. So basically I gave you a few examples of spontaneous emission so that you can understand how it relates to our daily life. And this process occurs naturally and is responsible for various real life phenomena, which I gave you an example. So here I would like to show you that spontaneous emission actually comes in different types. First one is what is called this is called excited state, or which is called a luminescence, coming from the Latin word lumen. So if atoms and molecules or molecules are excited by some means other than the heating, the spontaneous emission is called luminescence. Now luminescence has got further categories which I am not defining: electroluminescence and chemiluminescence. We go to the second part, which is the absorption. So if the excitation is affected by the absorption of radiation, the spontaneous emission is called fluorescence, again coming from the it should be fluorescent light. The second thing is sometimes molecules have a metastable level and continue to fluoresce long after their exciting radiation is turned off, and this is called phosphorescence. And figurines that glow in the dark are phosphorescent. Lasers via spontaneous emission, then during continuous operation. So it comes from this Greek word phos, which means light. The question comes that who actually first observed the phenomena of spontaneous emission? Let us look in the next part of our video. Who first observed spontaneous emission? And to your utter surprise, it is none other than our Dr. Albert Einstein. So according to the American Physical Society, the first person who correctly predicted the phenomena of spontaneous emission was Albert Einstein, and in a series of papers starting in 1916, culminating in what is now called as Einstein A coefficient. So here you can see this schematic diagram which shows the atom in the excited state, before the excited state, during the excited, and after emission, how it produces a photon. So spontaneous emission sets the scale for all radiative interaction such as absorption and stimulated emission. So atoms will only absorb photons of the correct wavelength. The photon disappears and the atom goes to a higher energy, setting the stage for spontaneous emission. Now when I tell that these are responsible for absorption and stimulated emission for all radiative interaction, we need to be very careful that spontaneous emission and spontaneous radioactivity, however, are not the same. Now it was Marie Curie's husband Henri Becquerel who is known for his discovery of radioactivity. So in 1896 he found that certain substances like uranium emitted radiation without any external stimulus. So this radiation is called uranium rays, and at the time was a form of spontaneous emission, but it is different from the spontaneous emission of photons from atoms and molecules that was later explained by Albert Einstein in the context of quantum mechanics. So spontaneous emission is basically the process in which an excited atom or molecule emits a photon without any external stimulus. However, spontaneous radioactivity, on the other hand, is the process in which an unstable atomic nucleus spontaneously decays, emitting radiation in the form of alpha, gamma or beta particles. So this process is the result of inherent instability of some atomic nuclei, and this is the process of a fundamental concept of quantum mechanics. Let us see in a tabular diagram what is the basic differences and what are the relation between spontaneous emission and spontaneous radioactivity, coming up in the next part of the video. So you see, this one is basically emitted from excited atoms or molecules. This is emitted from unstable atomic nuclei. Here these are responsible for emission of photons. These give rise to alpha particles, beta and gamma rays. No external stimulus, it is same over here. And here, this is the fundamental concepts in nuclear physics. This has got no direct relation. It is morely of a decay, so it has got no relation with quantum physics. So this is a good time that we understood the difference between spontaneous emission and spontaneous radioactivity. Let us not get confused. Now it is the time that we should understand that we have understood what is spontaneous emission. Now we need to understand that why classical physics actually cannot explain spontaneous emission. Coming up in the next part of the video, from here we will move into Schrodinger equation, why classical physics is unable to explain spontaneous emission. Now the definition of spontaneous emission actually tells this, which you have read earlier. So this is the process in which a quantum mechanical state transits from an excited energy state. So here you see I have made it bold, quantized amount of energy. So classical electromagnetism, as we know, is not quantized. Canonical quantization came much later. So classical physics assumes that energy exists in any amount, while quantum energy mechanics states that energy is quantized. The second thing, this leads to the absence of quantized electromagnetic field. That means the excited state atom cannot decay or cannot be measured to the ground state, which led to this conclusion that in order to explain spontaneous transition, quantum mechanics must be extended to a quantum field theory wherein the electromagnetic field is quantized at every point in space. So what we understand that directly from the definition itself, it is quantized. Classical electromagnetism cannot define quantization. In the absence of the quantized electromagnetic field, we cannot define it, and hence the electromagnetic field is quantized at every point in space in quantum mechanics. And now we see that spontaneous emission is what is called an irreversible process. Now, what is irreversible process and what is a reversible process? Just hold on, I'm coming to that part. But I need to explain you a little bit on the implications of spontaneous emission, because this is very important. Now, you see here that spontaneous emission, we have understood that the emitted photon can travel through space, interact with other matter, but it cannot actually reabsorb and come back to the atom at the same stage. In other words, we can say the process cannot be reversed to restore the atom to its original state. Now first, you see this is an atom, or say for example any subatomic particle. These are the two stages. So if I try to move from the higher stage, excited stage, to the ground lower stage, we can say this is permissible. But from this E1 stage, we cannot go back to the E2 stage. So that means that the probability the probability of an emitted photon being absorbed and to the lower energy state, and the emitted photon carries away the energy difference between the initial and final states. That means the emission of the photon is a very random event and the system does not return to its original excited state. We will come back to the precise understanding, but this is a understanding. Now when we talk of say for example a reversible process, now this is irreversible because it cannot come back. Now you might be thinking, then what is a reversible process? So an example of a reversible process is an idealized process in thermodynamics known as isothermal. So reversible, this reversible expansion or compression of a gas, in this process a gas undergoes a change in volume while being kept at a constant temperature. So reversible process which is coming back. So I would say isothermal expansion is a good example. But here, once the emission has taken place, the system has moved to lower energy state, the emitted photon carries away energy difference, and hence it cannot return to its original state. You might be thinking why it cannot return to its original state. It can go back. I will just show you in the next part of the video. So here you see there are three probabilities. First, this is an atom. It generates this I would say emitted photon. Now the probability of an emitted photon being reabsorbed by the same atom is very low. Why? This is because the photon has a wide range, as you can see, of possible directions, infinite range of possible directions in which it can travel, and only a small fraction of these directions will lead it back to the vicinity of the excited or the original state. So we can say that being reabsorbed by the same atom, the probability is very low because the photon has a wide range of possible direction. Second, even if the photon is reabsorbed by the atom, it is not guaranteed to return to the atom to its original excited state. Why? Because the photon may have lost some energy during its journey. Say for example, if we're walking for a long track, we lose our energy. So this is a kind of the same atom emitting the photon. So even if it goes back to this stage, it cannot come back to this E2 stage. So this is because the photon have lost some amount of energy during its journey, and it may not be so much energetic enough to restore back to the excited state. Finally, even if I assume that this photon has been excited, it emits a photon and it goes back to here. The question is that even if a photon does manage to reabsorb the excited atom to its original state, the reabsorb process is not instantaneous. What does that mean? This means that there is a time delay between the emission of the photon and its reabsorption, during which the atom can interact with other matter in environment. So this interaction can make it more difficult for the reabsorbed photon to excite the atom to its original state. So this actually shows the three possibilities. One, it has got infinite amount of directions. Second, even it comes back, it has already lost some amount of energy. And even the third condition, hypothetically, that it comes back to the original state, it is not instantaneous. So that means that during which the atom can interact with other matters, its environment. This interaction makes it more difficult for the reabsorbed atom to excite the photon to its original state. Now, here is a clean example further, that in quantum electrodynamics, which we call QED, remember that the electromagnetic field is not empty. Even when there are no photons in it, this is because the vacuum or ground state of the electromagnetic field can fluctuate and create and destroy pairs of virtual photons. So the vacuum or ground state of electromagnetic field actually can produce a lot of virtual photon, and these virtual photons exist in a very short time and cannot be directly observed. But here you see it interacts with other particles such as atoms. Now when in this diagram, when an atom is in an excited state, it can actually interact with virtual photons in the vacuum. This interaction actually caused the atom to spontaneously emit a photon, which is known as spontaneous emission. So you see the excited state and the ground state, this photon will again interact over here. So in an excited state, it can interact with the virtual photons, which this arrow is showing, and this interaction actually is what causes the spontaneous emission. Now we have understood what is actually spontaneous emission and how it happens. What are the implications of spontaneous emission, and why the photons and the subatomic particles cannot regain back to its original state. Now we come to the basic idea that you see here. This is basically the ground state, and this is basically the photon which is being emitted. And there are many different ways in which the electromagnetic field can transition from ground state to other state. So electromagnetic fields, because they have infinitely more degrees of freedom, or we can say possible configurations, than the atom. This means that there are many different ways, as I have shown here, in which the electromagnetic field can transition from the ground state to the state of one photon. And here it shows, but there is only one way in which the atom can transit from the excited state to the ground state. So here it is. There are so many ways in which it can go, infinitely many ways. So once the photon is emitted, it is very difficult for the atom to reabsorb, because there are so many other configurations, so many infinite amount of ways. So this is how the animation shows. This is the way, that there are many other ways. And but here there is only one way in which the atom can transit from the excited state to the ground state. So this actually explains why classical physics this actually explains spontaneous emission. Now we will come to the point that why classical physics actually cannot explain for spontaneous phenomena. Now you see, we know that classical physics, like entropy, is always increasing and an irreversible process, and this increase in entropy is associated with the loss of energy of the surroundings, just like the photon loses its energy during the journey. Now we know that classical physics actually cannot explain why entropy increases, because classical physics can describe process like spreading of a gas through a container, I mean to say, which are reversible process, but it does not offer any explanation of the processes exhibited in a favored direction. So from here what we can understand is that classical physics or classical system, if you can go back to my quantum mechanics videos also, you will see that it actually contains what is called a system which has got an arrow from A to B, and it can come back from B to A. But spontaneous emission, as you can see, these are basically what is telling, these states of emission are basically something which are spontaneous and which are not reversible. So if it is not reversible and it is something which goes beyond the scope of classical physics, then obviously it cannot explain it. And that is why you see here I have mentioned the example of the entropy. So why classical physics cannot describe it? Because classical physics cannot describe something which is an irreversible system, because that is the way classical physics and the entire philosophy of classical physics remain. Now the question is that what is the equation that was trying to describe during that time the quantum mechanical phenomena? I'm going to say what was the defining equation of the quantum mechanical phenomena. We will come to that, and we all know that is the Schrodinger equation. So in the next part of our video, what we will understand is that Schrodinger equation tried to explain spontaneous emission and why Schrodinger equation was unable to describe spontaneous emission, and from there we will move into the Lagrangian of the quantum field theory. So as you can see here, it was Erwin Schrodinger who actually defined this equation. I have taken two forms. So the Schrodinger equation, we can say it actually is a kind of a role of Newton's law on the conservation of energy, that it predicts how a system behaves. That means what would be the future ways where it will go, and the wave function will actually analytically predict what are the basic outcomes. And this is something which is equivalent to Newton's second law, F equals to ma. This was postulated in 25 and published in 1926. So we can say that Schrodinger equation gives a evolution over time of a wave function of the quantum mechanical characterization and of the isolated system. Now when we talk of F equals to ma, and Schrodinger equation is something which is directly related, or in some way it actually is an counterpart of Newton's laws of motion, it is a time that we should see that from Schrodinger equation how we can define it classically. Coming up in the next part of the video, I would like to take a very simple example that Schrodinger equation actually arises adapting the classical wave equation. Now we all know that the kinetic plus potential energy is equal to E. Okay. Now what I am trying to tell over here is that the Schrodinger equation here, this half mv square plus half mk square equals to E, this is nothing but an example of a simple harmonic oscillator. So here I am taking the conservation of Newton's law. And here we get F equals to ma equal to minus kx, and this is the quantum conservation of energy. This P goes into P, which is this one. I hope you can understand. And this is basically the transition of wave equation from physical variable to the form of operator, and this x takes place over here, and we get the Hamiltonian as something like this. So the form of the Hamiltonian operator is for a quantum harmonic oscillator. This was the classical harmonic oscillator. We move into quantum harmonic oscillator. So this actually defines this h psi equals to E psi, where h is the energy eigenvalue of the system and this psi is nothing more than the wave function. So this is just to define you that how we are moving from the classical nature of Schrodinger equation, taking the example of a harmonic oscillator. So what we do now is that we know that Schrodinger equation arises by adapting the classical wave equation to describe a physical system, where we can say that subatomic particles exhibit probabilistic behavior. That means they are bouncing around and they give the form of a quantum mechanics. Now the wave function actually describes, we know that the physical reality. That means particles in random motion leading to the dual nature of quantum mechanics, and the classical wave equation to describe physical system. Now this duality, both the deterministic from classical physics and probabilistic aspects arising from particles random motion, which we are going to say. Now we would assume that the average kinetic energy of a particle mass m in an environment T is something like this, and this v square is nothing more than the root mean square, which leads to this. And I've just mentioned that Vrms of lighter particles obviously is faster than heavier particles. Now if I take from internet, this is basically at 20 degrees Celsius, the de Broglie wavelength, the electron's mass is given something like this. So now from here what we get in is that if we try to take so we have seen this one, right? So this is actually the RMS, right? So this is the root mean square. Okay, so from here what we now take is that this psi xt is representing the one dimension, I would say, electron distribution function describing the electron is moving randomly within a wave packet. One dimensional electron distribution function which is moving randomly within a wave packet. Now at a particular time t, when the coordinate beyond the interval, so let us see this graph. This is the electron distribution function, you can say as an electron cloud. So what we say is that these are x1, x0 and x2. Now at a particular time when the coordinate is beyond x1 to x2, the distribution function, what happens, obviously would be equal to 0. And this equal to 0 means in the practical end this would become something like a standing wave. So the electron distribution function actually looks like a standing wave field which are tied to both ends of the string. Now the important feature that you need to understand, that the standing wave function is that the complex function, this xt equals to 0, can be written as the product of two terms, one of them depending only on x and another depending on t. So the complete electron wave function has this form as this. And in classical physics we know that if the wave travels along the x-axis, then the equation will be this. So we got that if it goes beyond x1 and x2, the function stands to be 0, and this shows like a nice standing waves where the ends are tied. And in classical physics where the waves are traveling along x, we get something like a wave equation is this. So we turn our page, so you know here that v is basically the speed of the wave function. Now we will take this equation forward in the next page, and from here what we try to do is that we are trying to divide we are trying to substitute this equation, the wave function, into this equation. And by dividing both sides by this one, this exponential minus I omega t, which is for the classical wave function, we get into this. And this equation, as you see, has only one variable x. Now you need to recall that from the Einstein hypothesis of the energy and momentum, what we get is E equal to h omega, and obviously P equals to h upon lambda, which is the amplitude. Now since the energy of the momentum of a photon, so here is the schematic diagram, the energy level, this electron is the high energy, so it moves from here to here. This purple arrow, let me show you again, this part, it moves from here to here. So since the energy of the momentum of a photon is originated from the transition of an electron from high energy level to a low energy level, the transition process must satisfy both the law of conservation of energy as well as the law of conservation of momentum. Therefore, we can use this equation, this one orange highlighted, we can use reasonably to apply this equation of the photon's energy and momentum to corresponding electrons' physical quantities, which ultimately leads to this, where omega is basically the angular frequency and p obviously is the momentum of the electron, and h bar we all know is the reduced Planck's constant. Now in classical physics we know that total energy of a system is the sum of the kinetic energy and potential energy, which can be expressed as this, and if I make this part going on the other side of the equal to, we get into this. Okay, when we turn the page and we finally found this one, p square equal to 2m e minus u. Okay, so from here when we go to the next page, we find this equation, and then we find this equation which we substitute. So this equation of classical physics, now I'm trying to substitute over this one, e minus u psi x omega equals to 0. Substituting this equation will actually gives to this h, this is a Planck's constant by 2m partial square psi x partial x square e minus u, that is the kinetic and potential energy, followed by the psi of x, which will be equal to 0. Now what is this equation all about? This is basically the one dimension time independent Schrodinger's equation for electrons. From here what we can finally take an kind of answer is that the Schrodinger equation is rooted in the solid foundation of classical physics. The equation is the natural result of applying deterministic classical mechanics to describe the system in which subatomic particles are moving randomly. And obviously here we can consider E as a free parameter, which obviously needs to be quantized, needs to be normalized. Now taking this, what we have now established is that the equation is basically a natural result of applying the deterministic classical mechanics into the system in which subatomic particles move. Now because Schrodinger's equation in nature, in philosophy, is a classical equation, although and it is non-relativistic nature, it faced some problems, which was actually I would say removed and being provided a better solution with somebody else. What is that? Coming up in the next part of the video. So here you see the Schrodinger equation which I have written actually is electron's energy level is quantized, electromagnetic field is not quantized, and most importantly we find that the equation is non-relativistic in nature. Now here is a point. Remember that spontaneous emission, whatever I explained with fireflies, neon lights, etc., these are all relativistic in nature. And here is this handsome gentleman, Paul Adrian Maurice Dirac. This Dirac equation actually was a kind of a relativistic equation in its free form, and it behaved and well predicted the spin-half massive particles which are called Dirac particles. So this is the Dirac equation. Don't ask me what is this all about. I will explain it in another video because it would require a different and a detailed explanation. So spontaneous emission is relativistic process. So Dirac equation is a good point for describing it. And why Schrodinger equation cannot explain the spontaneous emission? Because electromagnetic field in Schrodinger's equation is not quantized, equation is non-relativistic nature, and we just proved through mathematics that how classical mechanics actually is a form in terms of Schrodinger's equation. So that actually proves our point in terms why the classical nature of Schrodinger's equation was unable to prove spontaneous emission, what is spontaneous emission, and why we needed Dirac equation, which is you can say a kind of a relativistic Schrodinger equation to describe everything which is happening on the relativistic way. So now we come to the central part of our video, that why do we take Lagrangian in terms of quantum field theory. First we need to understand that why do we take Lagrangian. So here it is, the Lagrangian actually plays a crucial role in quantum field theory. That means what? It provides a powerful tool to describe and analyze the behavior of fundamental particles and forces. So first, obviously, covariance and relativistic invariance. It means that the Lagrangian actually is inherent under Lorentz transformation. Now, because special theory of relativity revolves around one fundamental concept, that is Lorentz transformation, Lorentz invariance, obviously the Lagrangian has to be in fit in hand in glove kind of a thing with Lorentz invariance, otherwise it is not. It also provides a unified framework both for describing classical and quantum mechanical system. The Lagrangian also provides a systematic way, what we call canonical quantization, which is basically quantizing the electromagnetic field. And as we will see now, that it actually derives the equations of motion, which are nothing but Newton's laws of motion. It is also something which carries the symmetry of conservation of laws like Noether's theorem, etc. And the Lagrangian is a central component of the path integral formulation. This part, Noether's theorem, I have already told, and it has got the consistency and predictive power of wide range of particles and interaction, especially which are happening in particle accelerator, etc. So this is why we need to understand Lagrangian. These are the reasons. Now let us see how we can mathematically find it. And obviously renormalization, I have already told that renormalization is required because E in that Schrodinger equation is a free parameter. So for the sake of simplicity, here is a path, a kind of a particle which is moving. So it will be a single dynamical variable, that is q of t. And a position of a particle moving in one dimension. It can be straight or curved, doesn't matter. So let us consider any smooth trajectory q of t, and this variable between times t1 and t2, regardless of whether the trajectory obeys or doesn't obey, does not matter. It defines the action integral, which is this. In this formula, this LQ comma q dot, which is the differentiation, is basically the Lagrangian. And we can take a simple example of the Lagrangian, that is here, that is kinetic minus the potential energy. Now in this context, for example, the Lagrangian is an ordinary function which is q and, okay, this would lead to this, yeah, q and q dot. And this q can be evaluated as q of t, and q dot obviously is dq of t by dt, simple. for the specific trajectory qt for each time in t. So on the other hand, you see this s is basically a functional of the entire trajectory, which is there in purple, which I have drawn. Now when we say that is a functional of the entire trajectory, that means what? That means it is taking the entire history of its motion rather than one particular time. So that is why it is a functional of the entire trajectory. Entire history of its motion is taken into account. Now let us consider all possible trajectories of qt which begin at the same value of q1 t1 and at the same value of q2 at time t2. Now the least action principle states that the trajectory which has the lowest integral, this one, among this set is classical trajectory, means it follows basically classical equations of motion, so Newton's law. Now we will see, for example, q bar t as a test particle. Let us consider this to be as a test particle, and we will consider its infinitesimal variation by this equation, which is del qt. And if the trajectory q bar t happens to minimize the action functional, or even say for example it becomes stationary, then the first variation of the action principle, this infinitesimal variation, happens to minimize this, then obviously del s has to vanish, it becomes 0. And this leads to the first variation. This is this equation. So we now get the del s equals to the integral of t1 to t2 followed by the del of Lagrangian of dt, that is the derivative in terms of time. So this is the first variation. Now what we do is that from here what we get is this one, because this is del f, this is for time. But that now what we see is that this q comma qt and q dot equal to dq bar by dt, which is actually what we call of the test particle, are basically derivatives of L. Consequently we get this one, and integrating we get this one. Now you see that due to this t1 t2, this is the initial and final condition which is fixed of qt1 equals to q1 and qt2, this should be qt2, yeah, qt1 equals to q1 and qt2 which is equal to q2. We must have del qt1 equal to del q t2, and it obviously must be 0, so that this one I am highlighting now in red, that the initial boundary term is vanished, it is killed off, and we are left with this. Now so from here we can say that we want this variation to vanish for any del qt, and the only way to happen is to make the expression inside the bracket to be vanished. So once we move to the next part, what we see that the derivatives L are actually, we get the Euler Lagrange equation over here. So the least action principle actually leads to the Euler Lagrangian equation, and L is basically evaluated in terms of the classical trajectory, and for example this one is basically the Lagrangian, where we get this value plus fq. Now let me explain this equation a little bit more. So you see the value of mq dot is given. Now this one is the Lagrangian for a non-relativistic particle. Remember, we are considering again here a non-relativistic particle, where this part is basically the kinetic energy and minus vq is basically the potential energy. And what we find from here is that the equation of motion, this one for the particle is this. So the equations of motion for the particle can be derived from the Lagrangian using the Euler Lagrange equations. And so once we move from here, so we are taking this one mq dot minus vq, this is actually the equations of motion for the particle of the Lagrangian, this one. So from here what we get, the equation simply denotes nothing more than F equals to ma, where F is the force and m is the particle's mass of the acceleration particle. So the Lagrangian can also be used to derive the conservation of laws of the system. Yes, and the conservation of the Lagrangian L would be this one, which is a constant, where this I, this one red one, actually denotes the generalized coordinate, and for the Lagrangian L equals to half mq squared dot minus vq, we get the conservation law as something like this. So this is actually the law of conservation of momentum, P equals to mq dot, where P is the momentum of the particle. So the Euler Lagrange equation, from here we see that it actually becomes this one, and then it becomes this one, which is nothing more than Newton's second law. So from this derivation, what do we understand? We understand that the conservation of momentum, the Euler Lagrangian equation directly from Lagrangian, can be deduced and go back to Newton's second law of motion. Now we are finally coming to the relevance that these equations of motion, Newton's second law from Lagrangian, why do we do this? The first reason is this one. It helps to unify the major two frameworks in classical mechanics. Newton's second law and the Euler Lagrange equation are equivalent, describing the same physical phenomena. Obviously, we move to generalized coordinates because the Cartesian coordinates we are moving to polar, spherical, cylindrical, lot of other weird kind of non-Cartesian coordinates. It actually extends to more complex system because it has Lagrangian is very useful to deal with many degrees of freedom, and obviously minimization principle, that is the Euler Lagrange equation, is derived from a variation principle. We further see that the mathematical simplicity is much more easier in the Lagrangian approach and more elegant than the using the traditional Newtonian approach. It is much more generalized because it deals with Feynman's path integral, and this is the summary. So because it provides a deeper understanding of the fundamental principle of classical mechanics, it offers a more flexible framework for solving problems, and hence most importantly establishes a classical a relation between connection between classical and quantum mechanics. So it is just not a mathematical curiosity, it is a practical and a theoretical tool for solving a wide range of physical problems. So now it's the time to take a quick summary what we learned. We learned a lot of things: the limitations of Schrodinger's equation, what is spontaneous emission, why classical physics cannot explain spontaneous emission, the classical nature of Schrodinger equation which led to the relativistic Dirac equation, the Euler Lagrange and the Lagrangian formulation in quantum field theory, from Lagrangian how we went to Newton's laws of motion, and why Lagrangian is very, very important. I would immensely thank you for those who are watching this video. If you like this video, hit on the subscribe button to get all the notification from Physics for Students. Here is my email ID which you can contact. This is my other channel on general theory of relativity, and you can further follow me on my Facebook, LinkedIn, Instagram and Twitter profile. Thank you very much. I will wait for your comments, and I will continue with the live classes as well as with the videos on quantum field theory, because we have just started learning this among this huge ocean. Thank you very much and see you very soon, and may the good Lord be with you.